Thank you for introduction. I'm Junichiro Matsuda, PhD student of Kyoto University. Uh, Today, I'd like to tell you about my recent result about spectral characterization of some properties of quantum graphs. So, the notion of quantum graphs was first introduced by quantum information theory 10 years ago, and it has been developed in the interaction between quantum information theory, operator algebra theory, and quantum group theory, non-commutative geometry, blah, blah, blah. And so it is a non-commutative analog of classical graphs. And adjacency matrix approach to quantum graphs was first started only 4 years ago. So spectral analysis on such quantum graphs has not so much been done yet. So I'm trying to do some spectral analysis on them. So other research already done about such spectral approach to quantum graphs. There's a research by Garnison. She did a spectral analysis on quantum chromatic numbers. But no other spectral analysis on quantum graphs is not yet done. So as a basic step for such approach, I generalized the following result for classical graphs. For the regular undirected quantum classical graphs, whose adjacency matrix is A. It is known that this graph is connected if and only if the degree D equals this number D degree. Connected if and only if the degree is the simple roots in the spectrum. If J is connected, and J is bipartite. If and only if negative D is in the spectrum. So I generalize these results for quantum graphs. So I'd like to explain what are these ingredients. So a quantum graph is defined to be a triple consisting of a finite dimensional sister algebra B and psi. That is a good state on B, so-called delta form. So more precisely, if we denote the multiplication map on B by M, and then delta form means that the composition of M and Hilbert adjoint of M is the sorry. So delta form is the faithful state on B that satisfies M composed with M dagger equals delta square times identity on B. So delta is a parameter for this state. So in classical setting, this finite dimensional system algebra corresponds to the function space over the vertex set. And this state corresponds to the uniform probability measure of space. And the final ingredient A is an operator acting on B. That is sure idempotent. And sure idempotent means A satisfies the following equality. We denote the sure product by this split, which is defined to be the normalization of M composed with A and the first entry A and the second entry A composed with the adjoint of M. So and this defines an operator from B to B, and it is called sure product of these two operators. So sure idempotent means this is equal to A. So in classical setting, so
when you said that psi has to be a delta form?
Yes. This is the form.
And how does the definition of delta involve psi?
So these coefficients.
Oh, the actual is the formula.
Okay. Yes. So in order to define the adjoint, we need the state. So we identify the GNS space of B, this psi and B, because it is faithful. So this is the definition of quantum graphs. So if A is so in the case of B is commutative, so by Gelfand duality, it is nothing but C of B. And in such case, this sure product is nothing but the entry-wise product of the matrix acting on this functional space B. For such quantum graphs, similarly to classical graphs, we can find several properties. For example, we say it is undirected if A is self-adjoint and A preserves the involution of B. So in classical setting, involution preserving condition is automatically satisfied because the classical adjacency matrix is a real valued matrix and involution is just the complex conjugate. But in quantum graph case, we need to assume this one in addition to self-adjoint condition. And we say that it is irreflexive or no loop. If the sure product with this adjacency matrix and identity operator on B is identity operator on B. So in classical case, sure product with identity operator is nothing but the diagonal entries of the adjacency matrix. So equals 0. So diagonal entries of the adjacency matrix is 0 if and only if the graph has no self loops. So we define no loops condition in this way for quantum graphs. And also we define the deregular quantum graph. As a if the adjacency matrix has the constant unit 1 as the eigenvector for eigenvalue D. And similar for the state psi. So this is another way for the classical characterization of regularity. So classical graph is deregular if and only if the constant function 1 on the vertex set is the eigenvector for eigenvalue D. So it's the analogy for the classical characterization. Any questions so far?
Why do you need like the side
Yeah. So because we do not assume this definition for undirectedness. So if we only consider undirected quantum graph, we just need this condition. But if we also consider directed quantum graphs, then we need to assume this condition too.
Right, the diagram. The same flavor, you need the left eigenvector, all of that, the right all of that.
Yes. Equivalently, this second condition says that A dagger has the eigenvector 1. So for example, for directed classical graph, we can consider a graph like this. Then this satisfies one condition, but does not satisfy the other condition. So in order to omit such an example, we need to assume both conditions. So we already explained those ingredients. So next we have to define what is connected quantum graph and bipartite quantum graphs. So in classical setting, we can say that so in classical setting, a graph is connected, disconnected if and only if there is a decomposition of the vertex set into two sets. such that there are no edges between two vertex sets. And it is bipartite if there is a decomposition of vertex sets. All the edges are between those two vertex sets. So naively, we might consider we might consider to define the bipartiteness and the connectedness by using the direct sum decomposition of the function space, such that the adjacency matrix is decomposed into of this form or but investigating in a concrete example for quantum graphs on M2, such a definition is found to be not well behaved. Such definition does not work well. So we have to find another definition for such connectedness and bipartiteness. And the correct picture for such properties is the homomorphism picture.
What do you quantum graph
And G prime. We define a graph homomorphism
from G to G prime?
The homomorphism to the opposite direction. Since we consider in the Gelfand duality the graph homomorphism and corresponding homomorphism between the function spaces the opposite direction. Since by the Gelfand duality, we need to consider unital star homomorphism. That that respects the edge relation. So I don't explain the indeed meaning of this equality. This operator is something like the following. If we consider graph with all vertices and edges like this, and consider graph homomorphism from this one to these two vertex sets, in that sense, these two vertices here and these two vertices here, then the adjacency matrix is of this form. It push forward, so this is the graph adjacency operator A, and it's push forward if the AF is the compression of such matrix to 1, 1, 2. in such a way, we can characterize the graphomorphism. And by using such graphomorphism, we can define the bipartiteness and the connectedness. The quantum graph is connected. If there is no quantum graphomorphism to from G to this classical graph with only self loops with two vertices. So in adjacency matrix, it is function space is C2 and uniform probability measure tau and adjacency matrix 1, 0 to 1. And we say it is bipartite. If there is graphomorphism, complete graph A2. Probability uniform distribution out. This is the matrix 0, 1, 1, 0. Okay. So in classical setting, this equivalence is easily checked because if there is such a graph homomorphism, then we can consider inverse image of such loops, and we can easily obtain decomposition of the vertex set into two disjoint groups. And similarly, bipartite graph. So by considering the inverse image of such graph homomorphism, we can obtain decomposition of vertex set into two groups, which has edges between only them, only between them. Then, by these definitions, I obtained that for the irregular undirected quantum graphs, quantum graph G with threshold state, say. Then we can show that this quantum graph is connected if and only if the degree D is a simple root in the spectrum, and if under the assumption that G is connected, and then G is bipartite in that sense, if and only if the negative D is in the spectrum of A. So this is the main result. Any questions so far? No. But there is a result about the degree and the spectral, the bound of about the bound of the spectrum by degree. But if G is a deregular undirected quantum graph, Then the spectrum of the adjacency matrix is included in the segments between negative B and D. So we can prove this result by using the graph gradient for quantum graphs. Okay. So as a future perspective, I'd like to tell you about the relation between quantum graph theory and random matrix theory. Then the approach to quantum graphs by random graphs, random matrices by Shervast and Vasilevsky. So they gave a way to generate quantum graphs by using the GUE random matrices. So, however, their approach is really random. So the obtained random quantum graphs has almost no symmetry. For example, they are not sure to be regular or so they are no. And so they prove that such their constructed random quantum graphs has trivial symmetry with high probability. So we seek for much better random construction of quantum graphs that generates a better that generates quantum graphs with some additional assumptions. Such that, for example, the irregular or Cayley or expander quantum graphs. So since such an approach is not yet done, so yeah, it's open questions we can do from now on. So, that's all for my talk. Thank you for your attention. Questions? Symmetric means this is this. Yes, because it always so wait, do you assume regularity? No. Then it's not sure.
Not true.
Okay. Not sure. I'm not sure. Yeah, good question.
you define expander for quantum graph? Because you got the graph expander model, you know it very well for classical graph.
Yeah, so it's a very good question. So yeah, now I'm working on Matt Kennedy and Michael Brennan about how to define expanders for quantum graphs. So classical expander graphs are defined to be a graph with spectral gap. So spectral gap means the largest eigenvalue D and the second largest eigenvalue lambda 2 is separated by some constant. One possible definition is a spectral gap, but it is not sure this definition is good in some sense. So we are trying to find the relation of this definition and other characterization of classical expanders, for example, using edge expansion or fast convergence of random walk and something like that.
Definition for your A.
Sorry. For expanders, we always assume regularity. So the largest eigenvalue is D, always. Yeah, it's really a question. Yeah, currently we have no result about it, but yeah, it should be investigated.
Any further questions?
It's also a very good question. Currently, universal cover of random graphs is not defined. So one problem is how to formulate quantum graphs for infinite quantum set. So, currently, adjacency matrix approach is only done for finite dimensional Caesar algebras. So, in order to define universal cover for quantum graphs, we need to generalize this definition to infinite dimensional case. Or so there's also another approach to quantum graphs by using the operator system in D of H. So such operator system approach is valid for infinite dimensional case. So it might be easier to formulate universal cover in terms of operator systems. What is not no. So in order to generate Ramanujan graphs, it will be powerful tool to use some quantum K-D graphs by choosing random generators. So since I and Gromada are discussing on how to formulate quantum K-D graphs in our setting, using the finite quantum groups. So using such tools, it might be possible to generate such good random Ramanujan graphs.
Questions? Next time. Junichiro again?